Hi, I'm Cyrus Hike of Oregon State's Team Triforce Senior Design Group. If you visited the 2011 Oregon State Engineering Expo or been lucky enough to stumble through Kelly Engineering Center on the right day, chances are you've seen our award-winning RF autonomous blimp. Developed by our team over the course of the last 8 months, this blimp is capable of flying with the aid of a Sony PlayStation DualShock 3 controller, as well as carrying out various environmental sensing functions. The DualShock controller adds a level of intuitiveness and simplicity that we feel sets our control scheme apart from other similar projects. Most of the wow factor from our control scheme comes from the DualShock's tilt sensing capabilities. By simply tilting the controller forwards and backwards, a user can control the pitch of the propellers, thereby controlling the altitude of the blimp. The velocity of the propellers is then controlled with the analog triggers found on the shoulder of the controller. In conjunction with the square button and the right D-pad, we have bidirectional altitude and velocity control. Now, although our manual control scheme adds a certain fun factor to the blimp, it's its external sensing capabilities that really set it apart from hobby shop toys. Here to explain some of those capabilities is the second member of Team Triforce, Thomas Shepard.
Oh, thanks, Cyrus. And you're definitely right about those sensing capabilities.
As you can see from our block diagram, the design of our blimp was split into 9 main sub-blocks. The blocks responsible for most of the sensing capabilities of the blimp are the navigation and collision blocks. The collision sensing is done using 5 separate LV Max Sonar ultrasonic rangefinders by Maxbotics. These sensors have a few different output capabilities, UART, analog, and PWM, but the output most relevant to our design is the UART. The UART signal sends out a series of bits timed to a certain frequency. The microcontroller reads in this series of 1s and 0s and converts them into integers corresponding to the length of the nearest object in inches. By placing these rangefinders on the front, top, bottom, as well as both sides of the blimp, we can detect objects before the blimp hits them, and use onboard logic to steer the blimp away and avoid any possible collisions. We have to be careful, however, to run the ultrasonic sensors one at a time, in quick succession, to avoid the ultrasonic wave of one sensor being received by a different sensor. These same sensors can be used to map out the interior of a building. When the ultrasonic rangefinders aren't busy scanning for an imminent collision, they store the distance between the blimp and any nearby walls or large objects. In addition to collision detection, we also have onboard accelerometers and gyroscopes that help implement a navigation system capable of tracking position. One of the main changes in our navigation system throughout the development process has been to shift away from using pure dead reckoning as our primary navigation source to using a combination of gyro positioning data and real-time propeller speed. Due to the relatively low acceleration of the blimp, as well as its tendency to tilt and wobble, the actual horizontal acceleration can be overshadowed by contributions from gravity as the x and y axes tilt slightly towards the Earth. This can lead to a very large integration drift, making a true dead reckoning system impractical for our application. For these reasons, we decided to switch our primary position tracking model to being based on the gyro heading in conjunction with propeller velocity. Using the propeller speed to calculate thrust, the current velocity to introduce a drag force to the model, and the gyro heading to gather the direction of travel, we can calculate velocity and position with much more precision, negating the integration drift that is such a problem in true dead reckoning systems. By using the accelerometers as secondary sensors, we can use their data whenever extreme acceleration values are present. This allows the blimp to account for collisions or unexpected movements and adjust accordingly, combining the sensing capabilities of the accelerometers with the consistency of the propeller thrust.
The blimp's sensing capabilities open the door for many potential applications, but none of that data is useful if the blimp can't transmit it back to the user. That's where our Bluetooth system comes in. Here to explain the Bluetooth is our resident Bluetooth guru, who's really done most of the work on it over the last few months, the third member of Team Triforce, Chris Stoddard.
As Cyrus mentioned, I was in charge of the wireless, and we originally thought we were going to do Wi-Fi, but after talking with Trailer and getting some advice from him, we decided to go with Bluetooth. We bought a Connect Blue module. It's a class 1, which means it can get up to about 100 meters range. We use this and then put that to communicate with the microcontroller using UART. We had a power, a ground, and a reset, as well as a transmission and receive line that communicated with the wireless or the microcontroller. And then we had some kind of hardware flow control lines that were data set ready, data transmit ready, clear to send, request to send, and these were just used in initializing the device and setting it up. After we had the device working, these were deactivated, but the pins were still connected to the microcontroller. And on the blimp on board side of our logic, we have a TI MSP430F 2410 microcontroller controlling all the onboard components of the blimp. We programmed this using C programming. We have 7.c files that control things from Bluetooth to navigation to the motors. This controller is a 16 megahertz controller, has 64 kilobytes of flash as well as 4 kilobytes of RAM that we use. The reason we chose this microcontroller was for the analog to digital converters as well as the buses. This particular controller has 8 12-bit analog digital converters, or ADCs, and that we needed to control various things from the blimp, as well as we needed 3 buses, an SPI that talked with the accelerometer, and 2 UARTs, one that talked with the collision and one that talked with the Bluetooth. We also needed lots of I/O pins for PWMs, switches, and multiplexers that controlled various aspects of the blimp.
To power the blimp, we used a 6.4 volt, 2.4 amp hour lithium-ion rechargeable battery capable of powering the blimp for 2 to up to 5 hours, depending on how fast the motors were being run. The battery was connected to 2 DC buck converters from TI, one outputting a steady 3.3 volts and the other a more beefy 5 volts. The 3.3 volt rail was used to power the navigation and collision sensors, as well as the Bluetooth module and the microcontroller. The 5 volt rail powered the motors. Each buck converter was capable of carrying up to 3 amps, which was much more than necessary for our design.
Now it would be fair to describe the microcontroller as the brains of the blimp, and the power supply as the heart. As for the muscle, well, let's take a look under the hood and see what we have going in the propulsion system of this blimp. There are really only 3 active components in the propulsion system. 2 propellers, mounted on a long straight axle, attached to a servo to control propeller pitch. Each of the propellers is then fed an analog DC voltage, allowing independent velocity control, along with a servo allows us to control both the velocity and the altitude of the blimp. This whole propulsion system is mounted onto a custom designed gondola attached to a 6-foot polyurethane blimp from Mobile Airships. Together, this makes up the total mechanical portion of the blimp bag itself. Now, speaking of Mobile Airships, that brings us to our first point for next year's seniors. Vendors do matter. We actually ended up ordering 2 different blimps over the course of the project, one from some company down in California, another, our second one, from Mobile Airships. And let me tell you, the difference in product was amazing. The second one didn't leak, it had good seals, it allowed us to actually test our product because we could fly. The second tip, be sure to order backup parts. 11 o'clock, night before final testing, we somehow managed to fry a microcontroller. We would have been totally out of luck, but fortunately, with the help of our TA and a little bit of fortune, we had a second backup microcontroller lying around, so we were able to get some help from our TA Justin, get it back on there, and be ready for final project testing. So those are kind of our tips, and this has been our blimp, and hope you like it, and have fun with your projects next year.